Yeah, so I'm going to be speaking today about some work I've been doing over the past year or so. Um, we've had a lot of excitement in the last sort of 5 to 10 years about deep learning, which has proved phenomenally successful across a lot of different domains. But something that harms its adoption in real world scenarios is that generally deep learning systems aren't able to communicate uh, their certainty or uncertainty estimation um, about a prediction. And so I've been kind of working on how we can make our deep learning systems do this. So I think the plan is to kind of talk through these slides for the next 20 minutes, unless we're changing timing. And then we're going to have a period for questions for 10 minutes at the end. I believe that people online can type in questions as they occur, and I'll address them at the end. So yeah, here's a sort of layout of the things I'm going to try to cover. I wasn't quite sure what sort of the background of the people that would be tuning in. So I've tried to kind of do everything from the sort of basics and introducing deep learning through to kind of arguing why we need uncertainty estimates, the normal philosophy we have around uncertainty, briefly talk about existing approaches, before finally kind of talking about my own sort of developed approach, the high quality prediction intervals. And then I'm going to close off by talking about some results of the developed method, and then one real world application that we're trying to use it in. So hopefully there'll be sort of a piece there for everyone, regardless of background. So I think this is one of my favorite diagrams around sort of AI and deep learning. So we had this period in going back to the sort of 1950s to through 60s, 70s, where there was a lot of excitement around artificial intelligence. There seemed like there was great potential. It didn't quite kind of come together at that point. So then researchers sort of started talking more about machine learning, which is more the sort of mechanisms and the tools that drive AI applications. And so they were sort of talking about that through the 80s, 90s. And then really it's this specific tool within machine learning called deep learning that sort of has really broken out from about 2010 onwards, that sort of caused all the excitement that we hear about. And interestingly, I think going to like 2018 now, we actually find ourselves using the term AI and artificial intelligence. It's sort of come around a full circle now, but they're all kind of parts of the same thing. And with this slide, I just briefly wanted to try to make the point that deep learning is itself not a particularly new idea. So I'm going to sort of use neural networks and deep learning interchangeably through this presentation. And neural networks are a thing that have been around for quite a long time, I think going back to like the 50s or 60s. And so I've got a sort of small diagram there trying to show what's changed. So the type of neural network that researchers were using in the 1980s would be sort of very small with one single hidden layer. So we've got a network there that's trying to predict, say, the time to an engine overheat. And so we're feeding in our dummy example, 3 predictive variables: engine temperature, fan speed, and coolant level. And then you want your neural network to basically learn a mapping from those inputs to the output. And we're not going to be getting too much into depth into how that sort of black box works. But we will be later talking about kind of the loss function that you use to train that output. But the point is, yes, so in going to the sort of 2010s, we find we're still using that same core idea. We've just got these bigger networks, which are able to learn more complex patterns. There's a few tricks that we learned along the way that are important for getting things working. But I think probably the bigger thing is the amount of computation, having computational power increasing, as well as the actual amount of data, given that we're sort of in the internet information age. And I think that, yeah, this is actually my favorite quote about deep learning. So you have this Google Translate engine, which used to run on a code base of about 500,000 lines of code. So it was basically a rules-based system. So it'd be very much say trying to translate from one language to another, and you'd sort of say, okay, if this word comes up, then change it to this other word, unless the second word is this, in which case do this, but in this case, etc., etc. And we're now increasingly moving to a situation where, rather than kind of having those expert systems that have been handcrafted, is we actually sort of use this machine learning approach where we just have a big neural network that's been trained on a ton of data, and it kind of learns these patterns by itself. So you can see there that the new engine, at least in the quote that I read, sort of reduced this down to 500 lines, basically deploying a deep neural network. So I'm now going to talk about uncertainty and why we need uncertainty estimates for certain applications. It's important to know that for neural networks, by default, don't output uncertainty estimates. They will output point predictions. So if you imagine this example here, so you're a factory manager and you have an algorithm telling you when your various machines are going to fail, and one of your algorithms pings you and it says, "Oh, this machine is going to fail in 60 days." There's kind of, it's not quite clear what you should do based on that information. Like, does that mean that we need to schedule maintenance immediately, or can we run the thing for 59 days? Which is before that 60-day limit. So that's kind of what neural networks like generally output, is just that single point estimate. What's a bit more useful is if you have like a prediction interval. So in the second example there, we've got an algorithm that says, rather than just this point estimate, it says 45 to 65 days with 99% probability. And the idea is then that you have a bit more information to play with about when exactly you should schedule that repair. So I'm going to be showing lots of diagrams like this over the next 10 minutes or so. So this is basically illustrating what I've just said graphically. So on the left side there, so we're facing a regression problem here where we have some input variable x, and we're trying to predict y. So x could be like age of machine or something, and y is the time that we're predicting to failure. And so on the left here, there you've got like a single point estimate for each x, and on the right you've kind of got this sort of boundary. So you've got a prediction interval. And yeah, so the argument is that for lots of real world applications, that prediction interval approach is a lot more useful. And so the question is then, how do we get to that sort of prediction interval approach? We need to consider things like, given x, what is the expected value of y? Then when we talk about certainty or uncertainty, the sort of mathematical way of phrasing that is what's the variance of y given x? So how sort of broad is that distribution? And you could predict like a full distribution, which is the probability of y given x, in which case you'd normally assume some form for the output, whereas a prediction interval doesn't assume a distribution, so you're just kind of outputting a y upper and a y lower estimate. So now I'm going to talk about a bit more philosophy behind how we think about uncertainty, and more generally how we think about regression problems. So there's sort of two fairly important equations there. So what we're saying is we have some x, which are your input variables. So that's like your engine coolant level, age of machine, that kind of thing. You have some kind of a noise term, the epsilon there, and we're trying to predict y, which could be like time till failure of a machine. And so what we want to do is we're trying to predict the uncertainty of y, which is that sigma y, that's your variance of y. And if you assume that the f of x and the epsilon terms are independent, then you can separate out the model uncertainty with the noise. And I'm going to show now a bit more intuitively what that model and the noise actually mean. So imagine you have some data like this that we have to fit a regression model to. And the question is, so yeah, if x equals 2, what's the certainty of our prediction? Well, we've got a few data points around there. There's a bit of noise, so there might be a little bit of uncertainty, but generally we should have, a good estimate of what that should be. When x equals 0, we haven't got any data in that immediate region, although we've got some not too far away. So, we should be a bit less certain about those predictions. And then also when x equals 10, which is somewhere way out here, we don't really have any idea about what that should be. And you want your systems to be able to understand this and output sensible estimates for that certainty. And so, yeah, so the first way you can think of uncertainty is in regions where I didn't have data or didn't have much data, my uncertainty should increase. So the fancy word for that is epistemic uncertainty. So you can see, in the middle there, we kind of got this increasing blue area where we don't really know what's happening, and then likewise either edge of the data. But in regions where we did have data, we sort of kind of know what's going to happen. And then the other piece of the puzzle is sort of saying how much noise you have in your data. So on the left-hand side, so both these plots are using the same sort of data generating function, the same f of x, but they've got differing noise levels. So on the left, we have kind of noise, like low noise levels. So it says for x equals 2, we're fairly certain of what y is going to be. On the right-hand side, if x equals 2, we're kind of not really sure. Y could be anywhere from 1 to -1. And so I'm going to term that data noise variance or aleatoric uncertainty. And so going back to our original equation there, we've sort of then now seen intuitively what the model uncertainty and what the data noise uncertainty are. I'm not going to go into too much detail about existing approaches for deep learning. There's a lot of good stuff out there, which I'm happy to take questions on this or give more information if anyone's particularly interested in. But yeah, so it goes back to the point that in the default form, a neural network will only output a single point estimate, and there's then they're not inherently probabilistic, and so there are then kind of various tricks or kind of different frameworks that you can use in neural network under in order to get uncertainty estimates out. So a couple that address the problem of model uncertainty, which was uncertainty in regions we don't have data, is you can have Bayesian neural networks where rather than having like point estimate for your parameters, you treat your parameters as distributions and integrate over those. A popular one in recent years is you can think of, there was a nice piece of work that showed that dropout, which is kind of a regularization technique in neural networks, kind of does something equivalent to variational inference, which is a type of Bayesian inference. You can also use ensembling, conformal prediction. I'm not going to go into all these in much detail. But then you also have specific techniques for estimating that data noise uncertainty. So the first one there, mean variance estimation or MVE, basically assumes a Gaussian distribution for your noise, and it predicts a mean and a variance from your neural network. The second one, low upper bound estimation, kind of takes a distribution-free approach that I've actually built on in my own work. So I'm now going to talk about the sort of specific method that I've developed, which I've called high quality prediction intervals for deep learning, which is, I call it a quality driven method. And so the philosophy behind the idea is that if you're outputting prediction interval, you basically want to shrink the width of the intervals as much as possible, so you don't subject to capturing some predefined proportion of your data points. So those are kind of the two pieces that we're trying to achieve with the same thing. So I mean, so for example, you could have a really wide prediction interval, like 0 to 1,000 days or whatever it is, that would capture 100% of your data, but it's not particularly interesting. So you kind of want to like squeeze it as much as possible while still capturing some proportion. And so here we've kind of gone back to a small toy network just to illustrate what we're doing here. So normally you'd just have a single output of y, which would normally be your mean. And so we're here proposing that we have two outputs for the network, a y lower and a y upper, which is your upper and lower bounds. So the mean variance estimation would have it would also have two outputs. One would be the mean and one would be the variance of the distribution. And I'm not going to go through the maths too much. This kind of just lifted from the paper, but I wanted to give a vague bit of intuition behind what I'm doing here. So we have this vector k, which tells you whether each point that you're predicting for has been captured or not. So it's 1 if you've been captured or 0 if not. And then c is just your sum of k, so that just says how many points your system's captured. And then we define these two important metrics. So you've got mean prediction interval width, which we said we want to be narrow, and so that's just summing over all your data points, just your predicted upper bound and your lower bound. And then you have prediction interval coverage proportion, which is the amount that you've actually captured compared to the total. So that kind of gives us the two pieces of the puzzle that we need to work with. I'm not going to go through the derivation here. Again, if anybody's interested, just raise a question and I'll sort of give a bit more intuition around that. But yeah, so based on those two pieces, we're saying our total loss function is going to be your average prediction interval width plus some term that we can ignore kind of these bits. The important thing is we've kind of got your coverage proportion in there as well. And so, yeah, I've named this the quality-driven method. And so imagine we're going back to this example where we have some data and we're not really sure what's going on in between the other things. With the proposed method, we get these sort of estimates where in areas where we had data, the prediction intervals kind of squeeze quite close together. And in areas where we don't have data, the prediction intervals increase and the uncertainty increases, which is what we aimed for. And the nice thing about this compared to, the big advantage of this is that it doesn't assume a distribution. So when we compare it to the MVE method, which assumed normally distributed noise, we've got some synthetic data here. So the top two images are normally distributed noise, and we find that MVE performs quite well on this. It kind of seems to capture the data as we would hope. The QD does okay, it gets a bit lazy and it doesn't quite bother kind of capturing these edges. But the advantage is when you say your data is exponentially distributed or has some other weird distribution, and I should point out in a real situation, you probably wouldn't know too well what distribution it is actually distributed by. So here we find that the normally distributed loss function kind of predicts some weird things. So it's kind of got this big area down here, which we haven't got any data for. So it's not really useful to predict something there. And again, QD kind of does a bit better. So we then, so in the paper that we wrote up about this, we produced some results. There's quite a standard experimental protocol that's been followed by sort of 3 or 4 papers that have all been kind of working on the same problem, where they use 10 open source data sets and they run experiments on each one. So I'm not going to go through all of them, but for example, you have Boston housing data set, which is quite a famous data set within machine learning. So you're trying to predict the house price, the price of a house within the Boston region, and you have input variables like number of rooms, square footage, this kind of thing. And then some more interesting ones, you have like wine, where you're trying to predict the wine quality based on, again, certain covariates, to do with like color and texture of the wine. And so what we find, so for these experiments, we ask the systems to output 95% confidence intervals. And so we got the QD method in red there and the MVE in blue. And we find that generally the QD method was kind of more closer to predicting the target 95%, which was good. And then we also have statistics here on the mean prediction interval width, which we said we want that to be as small as possible. It's a little bit difficult to kind of compare. You need to look at it in conjunction with the coverage proportion, because obviously if something covers a lot more, you'd expect it to have wider intervals. But yeah, when we did some further analysis on this, we found that the QD method offered about a 10% reduction in prediction interval widths. And yeah, here's sort of a nice diagram for that Boston house price prediction task, where, I mean, we can only show one covariate here, which I just picked one randomly. So say this is like square footage or something, or it wouldn't be square footage, but something like that. And what we find is that, yeah, the prediction intervals that we're producing generally kind of capture their points. So you can see this one in the bottom right is quite tight, and it's sort of captured that point quite nicely, compared to, say, something like the top left one here, where we had quite a wide prediction interval, so kind of knew it was uncertain, and we have actually missed the point in that case. And then the right-hand side is just these points ordered sort of small to large to kind of give a different view of it. And so this is the paper that we've written. It's on arXiv. It's just been accepted at ICML, which I'm very happy about. I'm going to be presenting that next month. And I thought the last thing I wanted to talk about just for 1 minute is a real world application. So we're working with one of the partners on this. They gave us a warranty database going back a couple of years. And so with a warranty database, you have things like your product type, perhaps the region, like where it was built, also maybe like the specific comment by the technician as to what went wrong, and a bunch of other things which I haven't shown. And this is a very human-intensive task to have somebody actually manually check all of these and decide whether they should be paid or not, or queried. And so one of the ideas is that perhaps we could automate this assessment to some extent, or I should probably say augment to some extent. So you feed in the variables, you kind of cover up the price, and you ask the system to predict the amount that's being claimed for. So you kind of come up with a prediction interval for that, and then you compare to what has been actually claimed for. And the idea is that if your actual claim falls within your expected claim, then perhaps you don't need to review it with kind of so much resources. Whereas if it fell well outside, so in this example, we kind of got an extreme example there, you definitely would want to review that. And so this is kind of something that needs to have more work before we get any results. But that's kind of an application in the real world where it could be used. And that brings me to the end of my slides.